Hello Chem 1B, this is chapter 16, lecture video 3, and we're going to talk a little bit about other P scales, right? So we talked about pH in the last lecture video. This lowercase p just means power scale. So if you see anything like P and then X, it's really reflecting the same thing as pH, but with a little bit different definition, right? So for instance, anything X here is just the negative log of that X, right? So if we wanted to calculate, for instance, pKw, since we have pKw, this would just be equal to the negative log of kW, right? And the same thing is true of any other type of system. If we have P shoes, then we take the negative log of the concentration of shoes. So this is kind of how we deal with logarithmic scales or power scales. Now, we know that we have this equation here, right? So we can take the negative log of both sides of this. And if we do that, we get this expression. Negative log of kW, like I just said, is pKw. And the negative log of all this is, we can break that down a little bit more in the next bit. And the negative log of 1 times 10 to the negative 14 is just 14. So if we break this down a little bit more, we can separate this thing up into this. Negative log of H3O plus minus negative log of OH minus is equal to 14. Well, this whole thing is effectively equal to, this bit is pH, and this bit is what we call POH. So really, pH plus POH is equal to 14. Now, I will provide this equation on your exams. However, you should kind of realize that this thing only works at 25 degrees Celsius. So let's calculate the pH of an H3O plus solution, right? We talked about this a little bit earlier. In the last lecture video, negative log of H3O plus concentration is equal to pH. So if I want to solve for this, all I do is take the negative log of the H3O plus concentration I was given, in this case 0.015, and that will get me my pH of the system. In this case, if we plug that into our calculator, we get that the pH of our system is equal to 1.82. All right, so let's move on. So we know how to do pH from H3O plus, as in the last video, but now let's talk about how to get H3O plus from pH, because there's a backwards measurement as well. You need to take the inverse of the log function, which in this case is just going to be equal to 10 to the power of negative pH. So if I know, for instance, that the pH is 2.32, I can put 10 to the negative 2.32 to get my H3O plus concentration. And if I plug that in, I get 0.00479 molar as my H3O plus concentration of this solution with a pH of 2.32. This is going to be very important to later problems that we do, to be able to go both directions. So let's just very briefly go over acidic, basic, and neutral solutions. Now, many of you may have learned prior to this that acidic solutions have pHs less than 7, and basic solutions have pHs greater than 7, while neutral solutions have a pH of exactly 7. And while this is all true, this is really only true at 25 degrees Celsius. And it's not really the definition of these solutions, more so just what we see with pH. An acidic solution contains an additional amount of H3O plus in solution besides what is formed from water. And because of this, we know that at 25 degrees Celsius, if our solution is acidic, the H3O plus concentration in solution has to be greater than 1 times 10 to the negative 7, which thereby means that the pH is less than 7. In addition, in acidic solutions, you should know that H3O plus concentration is larger than OH minus concentration. This is pretty much everything in reverse for a basic solution. In a basic solution, we have an additional source of OH minus. Therefore, our H3O plus concentration is actually less than 1 times 10 to the negative 7. Our OH minus concentration is greater than 1 times 10 to the negative 7. And our pH is greater than 7. In a basic solution, our OH minus concentration is always larger than our H3O plus concentration. Finally, we have our acidic solution, or neutral solution, sorry. Neutral solutions have no additional source of H3O plus or OH minus except the autoionization of water. And because of this, our H3O plus concentration and OH minus concentration are equal. And they are both exactly 1 times 10 to the negative 7, again, at 25 degrees Celsius. And the pH, again, at 25 degrees Celsius for a neutral solution is pH 7. The pH of a neutral solution is actually temperature dependent because Kw, which is an equilibrium constant, is temperature dependent and it changes, and therefore what is the pH of a neutral solution changes with temperature as well. So here's just kind of a general gist of the pH scale, and you can kind of see that as our pH goes down, our H3O plus concentration goes up. All right, and at the same time, as pH goes down, POH kind of has the opposite respect, right? As one goes up, the other goes down, and vice versa with pH and POH. The same thing is true, the same relationship that we saw with H3O plus or H plus and pH is true of POH and OH minus, right? As the POH goes down, the OH minus concentration goes up. And so there's just some kind of cool stuff here, right? Rain generally is slightly acidic, right? Egg whites, human tears, salt water generally are pretty much almost exactly neutral. Slightly basic, if anything, but that could be due to temperature, to be honest, in a lot of cases. Soda and vinegar are super acidic, usually at a pH of less than 3. And if you really want to gross yourself out, you can YouTube human teeth in soda, and you can watch the tooth dissolve. Our teeth are made up of a lot of calcium solids, which generally are more soluble in acidic solution. And therefore, when you drink acidic beverages, you actually probably have more cavity formation because of the fact that they dissolve your enamel and teeth. Ammonia, household cleaners, usually are on one side of the pH spectrum. Either they're incredibly acidic or they're incredibly basic. Most of the time, our cleaners tend to be on the basic side. All right, so this is the end of this video. If you have any questions, please let me know in my discussion sessions or my office hours.